Hello class, this is your first video, so you should be on page 3 of the notes. We're going to start with the video about more z-scores. So basically, more practice of the last example we just did in class. So our goal here is we're competing in the long jump, and our friend is competing in the mile run. So as you can note, the long jump is done in feet, and the mile run is done in minutes. And we would like to figure out who did better, us or our friend. So very similarly, I gave you the means, the standard deviations, and the actual values. And our goal is just to figure out who did better. So one of the first things we should do is talk about each of the events. So let's first talk about the long jump. So how do you win the long jump? So by winning the long jump, you're the person that jumped the furthest. So in the long jump here, higher is actually better. Right, so if I jumped 20 feet and you jumped 22 feet, you did better than me because you jumped further than I did. However, if we look at the mile run, the person that wins that is going to run it the quickest, or is going to run it in the shortest amount of time. So in this case, actually smaller is going to be better for the mile run. Now that I know what is actually better for each of my events, I can look at ours and our friends' values. So if we look at our value for the long jump, we jumped 22.48 feet. The average was 22.23 feet. So we did do better than the mean because we jumped further than the mean. Now if I do something similarly for our friend here, they ran the mile run in 7.61 minutes. The mean time to complete it was 8.65 minutes. So they were quicker than the mean. And again, quicker is good here because that means it's a smaller number than mean. So they also did better than the mean. So by just comparing them to the mean, we do not know who actually did do the best because we both did better than our corresponding means. So what we're going to need to do then is actually look at our z-scores. So first, as a reminder of the z-score formula that we learned in class, z is y, which is our observation, minus mu, which is our mean, divided by our standard deviation, which is sigma. So let's first do this for our long jump. So in the long jump, our z would first be our actual observed value. So we jumped 22.48 feet minus the mean distance jumped, which was 21.23 feet, and dividing by the standard deviation, which was 3.45 feet. And if we do the math here, we're going to get a positive 0.36. Now why was it positive? Well, 22.48 is bigger than 21.23, so we are above the mean. Versus if it was negative, it just would have meant that we were below the mean. Let's also interpret this number to make sure that we understand what a z-score is actually measuring. So this means for us that we jumped 0.36 standard deviations better than the mean. And here again, better is because we were actually above the mean, and the higher is better here. Now if we did something similar for our mile run. So again, now we'll calculate our corresponding z, which is then our observed value, which is the 7.61, minus its corresponding mean of 8.65, and divided by our standard deviation of 2.11, and that's going to give us a negative 0.49. Now this one is negative since 7.61 is smaller than 8.65, but here negative is actually a good thing because that meant that we were smaller than average, or in a sense here faster than the average time. So negative is actually good for the mile run. So we could say then that our friend ran 0.49 standard deviations better than the mean. Now, where did that negative sign go? That negative sign went as soon as I put this word better, right? Because we said smaller was better. So negative actually is a better value, versus this would have been a positive 0.49. Our friend actually won that much slower than the mean, or worse than the mean. So we aren't using the negative inside the interpretation when we chose the word better. So now comparing the two, who did best? So we jumped 0.36 standard deviations better. They ran 0.49 standard deviations better. So overall, who is best? The mile run is going to be best because they performed more standard deviations better than average. All right, now doing the same thing with a similar example, but with a different goal in mind. So with example 2, we would like to figure out which test score is more unusual. It's a little bit different than saying that someone was better. So we have a 48 on a Stat 205 exam, or an 83 on a Chemistry 115 exam. Well, so we have to know what those look like. So Stat 205 exam scores have a mean of 73 and a standard deviation of 16. Chemistry 115 exam scores have a mean of 61 and a standard deviation of 12. So let's first just sort of write down what we know. So from Stat 205, we know the mean is 73, and we know the standard deviation is 16. From Chem 115, we know the mean is 61 and the standard deviation is 12. So we have different means and different standard deviations. We're also given our corresponding value of y. So for Chemistry 115, we got an 83 on that test, versus for 205, we got a 48 on that test. Now, of course, if we were to try to figure out who did better, well, they performed below the mean, they performed above the mean, so it'd be pretty easy to see that the person did better on the chemistry exam. But we're not asked for better, we're asked for what's more unusual. So to understand what's more unusual, let's first talk about what we would expect usual to be. The most usual value that we would expect to have happen is the mean. Right? I mean, so if the average is a 73, that's kind of what we would expect a student scored on the test would be a 73. So our usual would be the mean. So what would be unusual then would be far away from the mean. Now, I'm not saying which direction, just away. All right, so then what I'm looking for when it comes to my z's, well, a usual value being a mean corresponds to a z-score equal to 0. Because as we learned in class, z-scores have a mean of 0 because we expect it to be the mean. Or going back to our formula we had here before, in this z formula, if y actually was the mean, so if I had mu minus mu, I'm going to get 0 for my z-score. So that's what we would expect to see happen. So what would be unusual would be a z that is far away from 0. So whichever z I get that's furthest from 0 is going to tell me that score was more unusual. Okay. So now let's actually do our math. So let's do our z for our 205 student. We take our value of y, which was 48, minus our mean of 73, divide by our standard deviation of 16, and we get a z-score of negative 1.56. So we could say then that this score was 1.56 standard deviations below, since it was negative, average. So they did below average on the test. versus for our chemistry student, we calculate our z-score. So the value of y was our 83. The mean was a 61. The standard deviation was 12. We would get a positive 1.83. Now, why was this one positive? Because they did better than average. So we could then say that this score is 1.83 standard deviations above average. Alright, so now going back to looking at what my goal was. I'm trying to figure out what was most unusual, which is the z that's far away from 0. So when I go down here and look at my two z-scores, I look at my negative 1.56 and I look at my 1.83. Which of those numbers is furthest from 0? So we would actually say that our Chemistry 115 exam is more unusual because it is more standard deviations away from the mean. Again, notice when I say the word away, I don't care about if it was above average or below average. All I care is that it was away from the mean. Alright, so there was a couple more examples of using z-scores to figure out how to answer a question when you're working with different means and different standard deviations.